Okay, so good morning, everybody. So just a reminder before we start the morning session that we had a slight change to the second session this morning. So we won't have a talk. We'll have hopefully a very informal session where people talk about some archives that they've been using in Cambridge. Before we get to that, though, it's a very great pleasure to introduce Amira Moeding, who's based here in Cambridge, and she's going to talk to us on practices of prediction, big data as foundation of modern AI.
Well, can you all hear me? Great. Thank you so much for having me. Thank you so much for the opportunity to speak here. I should start with a couple of disclaimers. So first of all, I'm not strictly speaking a historian of mathematics. I'm usually based in the Department of Political Thought, and I think that will be kind of like visible throughout my presentation. Of course, if you look at the title, there is mathematics in here, right? But yeah. And then the other thing that I should say is that all of this is very much a work in progress. So it is part of my yet-to-be-finished PhD project, in which I attempt to trace the history of big data. So I would be extremely interested in all your comments and questions, because again, I might still incorporate them. What struck me when I started researching the history of big data was how big data first denoted a problem, according to actors. More data than a system could handle, and from the 1980s onwards, but in particular in the 1990s, became what actors called an empirical approach, or a method to build artificial intelligence applications, first in language processing and later in image recognition, and how it allowed statistical or even probabilistic approaches to be implemented in connectionist models. That is, artificial neural networks, and how then turned to become, if we believe writings in particular from the 2010s, a solution to everything. So from a problem to a solution to almost everything. That big data became an approach to AI coincides with the birth of modern artificial intelligence versus good old-fashioned AI, and it connects big data to complex phenomena, or rather what was constructed as complex phenomena by the industry. Big data here, I argue, appears as a way to make complex phenomena accessible to computer systems. Big data as an approach is a way to bring unruly, illogical phenomena to computers. Then big data becomes a way to render the world computational, that is, computer readable. So this is what the talk is going to be about. Big data is the approach to or method to create what Stuart Russell and Peter Norvig in the famous textbook from 1994 call modern AI, as a way to render what the industry, again, calls complex phenomena computational. Big data, I believe, might be best analyzed from a phenomenological perspective, precisely because of that, both as a new phenomenon, but at the same time establishing the computer system as a perceiving and processing more than calculating entity. Therein, centering, as one of my actors put it, the nature of the machine, naturalizing the computer as a tool for data processing instead of perfect rational formalism. Here, the big data approach impacted scientific values and standards in computational fields, such as computer vision or natural language processing. And so the three key questions that guide the presentation are: what, if anything, is big data? And how has big data changed what data are? How did big data become a successful approach to building AI applications, or rather what we call artificial intelligence today, right? I think that shifts. And how does big data relate to ideas of complexity, or rather complex phenomena, as one of my actors puts it, therein reconfigures the nature of the computer machine. So what is big data? The question, what if anything is something, what if anything something is usually not considered a historical question, but an ahistorical one. What something is and really is usually is not supposed to change. If we ask what an atom is, we only get the answer right if the answer holds over time. We could have the same idea of data, big or not, and we often find a similar idea of data that even involves the atom as an analogy or metaphor. Data are often seen as the atoms from which we build facts, the smallest piece of intelligible information we have access to. In the following, I would like to destabilize this idea of ontology by drawing on Ian Hacking's notion of historical ontology, and from there get to the first part of the presentation, namely actually discussing how big data became a thing, and the many ways in which big data has existed and shaped our world, and even, I'll argue, our sense of self. That's where the politics come in, right? So Ian Hacking takes this idea of historical ontology from Foucault and notes that Foucault used it about twice, and I just find that very charming. He writes, "I am comforted in the fact that historical ontology is not one of the terms on which Foucault seems to have laid much public emphasis. It is possible that he used historical ontology only during one particular visit to Berkeley in the early 1980s, about the same time he gave an interview that also referred to historical ontology." So after registering his comfort in the fact that historical ontology is a notion possibly not very important to Foucault and likely so far fairly unnoticed in Foucault's scholarships, he puts this idea at the center of his way of doing or narrating history. He dares us to ask what the conditions are for something apparently new to come into being. Nothing, it seems, in Hacking's view is just something. Things are what they are, only in a certain space and at a time. That does not make them less real, less constitutive to ourselves as subjects, the world, or our ways of perceiving the world, of course. In his most, I think, famous work, at least to me, most important work here, The Taming of Chance, Hacking teaches us that chance and probability, basic mathematical concepts, only took form vaguely recognizable to us today in the 17th century. Did chance not exist before we had the formal means to define it? Of course not. However, chance took many forms: miraculous intervention, unruly nature, and most importantly, luck. When chance, at least partially, took another and importantly formalized shape, it impacted not only math and the sciences, but by being applied to a variety of phenomena and including people, these phenomena included peoples and populations, it changed government and practices of subjectivation as well. Chance, however, in Hacking's telling, did not just emerge because of mathematical refinement or possibly something that we might see as a theoretical discovery, by which we just learned something new about chance, again, as a timeless mathematical construct. Instead, chance and probability, in Hacking's view, only become possible because society transforms, allows for new forms of inquiry and seeing the world, and these changes are mirrored back to mathematics, where then new things can be discovered and become visible about these concepts, and then they, in turn, as I just said, impact us again. And he actually ties the emergence of chance directly to what he calls an avalanche of numbers, also in the 17th and 18th centuries. What is discovered formally about mathematical concepts, then, in Hacking's view, is intimately linked to how these formalisms are used and employed. Yet using something, of course, always happens within a context and often stems from a need or want that is itself an expression of historical circumstance. Historical ontology is Hacking's attempt to come to terms with to what degree our practices shape the limits of our concepts and understanding and vice versa. The question for Hacking, then, is not primarily how do we know phenomena, although that is a huge part of the next question, but rather, I think, how do we create them? And in that, his account is particularly useful to me. Hacking here, following Foucault, limits his concepts. Hacking here, following Foucault, limits his concepts of historical ontology to the question of how things and categories of knowledge are created, which overlap with ethics. That is, with how we constitute ourselves and with power understood as and that is Foucault, right? Institutions, technologies, practices, and ideas that constitute us and in which we are made to operate. So a new things emerging with a new concept is only possible within what Hacking captures sometimes with the analogy of an ecological niche or within certain circumstances. Hacking urges us to go beyond the dichotomy of reality and social construction and take the concepts that shape us, and shake us maybe at times, as both radically historically contingent and therefore powerful and very real in creating ourselves. In the following, I'll attempt to show, more than explicitly argue, that big data can be analyzed as a historical thing that could in fact only come into being in a specific industrial and Cold War niche. To become fully successful, it will need the internet, and in particular, the internet conceptualized no longer as a medium of communication, but as a database. I hope to show that big data indeed has become something that shapes our conception of self and the world on a fundamental level, and that the practices around big data, even beyond the state and government, now shape us as subjects. Moreover, the concept big data, more than a thing, has come to denote since around 2009. First, I think a somewhat dubious claim to objectivity or some form of knowledge beyond theory. And as I noted already, it denotes a method or an approach to creating intelligence. My question is, are both linked? Or is there something in the way we use computers to work with and create big data that creates a powerful conception of immediacy that gives rise to the claims around, as some of my actors puts it, even a God's eye view suddenly on the world, or theory freeness? Now, depending on how we see the world, there has always been a large amount of data, and there has been and still is way more data than we can process. That is in particular true if we see the world as in some sense consisting of data, maybe even in a similar way as it consists of atoms, which recently seems to have become a popular idea, and that is the idea I'm kind of tracing. However, big data only becomes a relevant thing in relation to the machines that process it, that is digital computers, and as I said, I'm in particular interested how big data became a foundation of intelligence, artificial or not, and how in that process it also changed how computers were perceived and how complex phenomena were brought to the computer or became objects that could be rendered predictable via computing processes. And that process that unfolds in an explicit way from the late 1980s onwards, data, AI, and computers all changed their character, and so certainly did many of our institutions and gradually our sense of self. Okay, so what is big data? So according to actors, the notion of big data came out of places where we had an abundance of data. Big data is also connected to the gathering of mainly new image data, a strong idea of inference by proxy, and the problem of making sure that the data could be processed so that it would be relevant to the question or problem posed, which is when data became big, that is when it remained unprocessable or unreadable. To me, that is an interesting idea in itself, that there is such a thing as data independent of its context of usage or readability, because as philosophers of science tell us, there are no data, and historians as well, there are no data independent of theory, context, or interpretation. That is, if you implement the same data into different contexts, they often take on different meaning. Data, as we understand it today, at least in English, is an effect of 18th century empirical sciences. So I'll now talk about what data is. So, or how it becomes what it is. Dan Rosenberg teaches us that until the late 17th century, the notion of data is used where we expect it least. Theology and mathematics, mainly geometry, pertaining to everything that, as the Latin suggests, is given and does not require explanation or proof. Data were not created or acquired or searched or collected. They simply were what was true beyond doubt or question and already evident. The notion of data was employed to refer to axioms in mathematical proof, God's word, the premises of an argument. In being what was clearly given or uncontroversial, data were also fundamentally not interesting, and so according to Rosenberg at least, the word was not much in use. Rosenberg notes that to him, this makes data a rhetorical concept, in the, again, classical sense of the notion rhetorical concept, as simply denoting a specific part of an argument. He distinguishes it as that from an epistemological idea or an ontological category. Gradually, during the 18th century, the use of the notion of data increases, partially because its meaning underwent a radical change. By the end of the 18th century, data became, as Rosenberg writes, the result of an investigation rather than its premise. The data, the data could move from being the end point of a query rather than its beginning has much to do with the development of the empirical sciences and with the idea that things such as air or societies should be the object of experiment. And it is in the laboratories of Francis Bacon and Joseph Priestley that data becomes representational of phenomena and the result of careful experiment. That is for the English-speaking world, of course, right? Bacon does not yet have or use the word data to describe what he learns. Yet, and I think that's a case in point, the term is back projected by his 18th century commentators to describe Bacon's experiments as a form of data collection or generation. Priestley uses the notion of data for numerical abstractions he collects in tables to analyze, as he puts it, different types of air. So data here is created through experimental practices and not obvious. It appears only in its written or depicted form and is dependent on theoretical hypotheses, the setup of experiments, as well as laboratory equipment and written record to emerge. It is not given. Data then only becomes apparent as mediated through, as I just said, numerical abstractions and tables or graphs. Data are no longer given, they are highly mediated and carefully created entities. Hence, data in the modern sense, as historians Paul and Edwards, and again Dan Rosenberg remind us, are things with materiality, and I think that is now kind of important to point out. Data, however, usually are not seen as material, as the definition by the Oxford English Dictionary shows, that simply, and here we come to the current definition of big data, equates data with fact. However, as Rosenberg notes, if a fact is proven wrong, it is no longer a fact, while data, wrong or right, remain data after their generation and as long as they are stored and we still have a way of reading them. If you're doing the history of 1980s computing, that is sometimes hard, still finding means to read data. This is what ties them so strongly, data, I think, to the context of the laboratory and to the fact that they are not only the building blocks of fact, but of phenomena, as we can perceive them, either as experts or in sense data through our own senses. They represent or misrepresent something in the world, but in that they become the most fundamental insight that we can have about something since the emergence of empirical sciences. Philosophers and scientists have therefore dreamt of data that is detached from its context of generation and use, from models and theory, and importantly, our perceivable senses themselves. The history of the 18th century aside, and arguably here already the emergence of a new phenomenon, namely data, as we understand it, the term only becomes ubiquitous in its modern meaning as something that describes, accurately or not, phenomena and provides insight about them by the 20th century with the advent and then prevalence of automatic data processing. In a sense, I believe we are moving back to pre-18th century uses of the notion of data. At least in one reading of big data, the term seems to suggest or even promise a path beyond theory and more direct access to phenomena. As Chris Anderson writes in his wildly oversighted piece, titled "The End of Theory, the Data Deluge Makes the Scientific Method Obsolete," that with enough data, the numbers speak for themselves. Which brings us to one meaning of big data, the idea that the sheer quantity of data, and one should point out probabilistic inference, have made the world fully readable. However, not to us, to computers. Here data assumes a sense of givenness again, something that provides an unquestionable fundament. In this, it keeps while doing this, it keeps a strongly technologically mediated character and even the ontological character, but becomes detached from human experience, the senses, and even, at times, if we believe commentators, becomes unintelligible. The latter, I believe in particular, might give data this feeling of something that transcends questioning and therefore lies again outside the realm of argument. I'll return to this point when I discuss statistical versus probabilistic approaches to AI. However, it is important to note that, of course, data still are made, and that by no means, as Anderson suggests, theory-free. Rather, it might become apparent that theory might have changed its character as well. The context of origin for big data was Cold War so-called big science, the insanely well and importantly mainly federally funded scientific laboratories that emerged around institutions that inhabited the space in between military or other state agencies and research institutions, such as public or already private universities. To have and even just to generate a lot of data was and actually is expensive and requires a lot of human labor, which was usually at the time done by women. And now I think we've relegated this labor to the south. Here data creation is seen as trivial, no longer the work of experts, which also strikes me as an interesting breakaway from the 18th and 19th century sciences. NASA and the Jet Propulsion Laboratory seem among the foremost places where by the mid-1960s big data had emerged as a problem. Big data was by no means a formalized concept, but a way of speaking between colleagues. However, everybody knew what it meant. It meant basically that somebody had to pre-sort data rather laboriously before it could be prepared for computer analysis. Other than that, it just remained inaccessible and took up a lot of space. When I spoke to Alex Pentland, today one of the foremost advocates, and on the previous slide was two actually of his books, one of the foremost advocates of big data in politics in the state, he remembered the first time he had big data was when he worked in image recognition for a small outpost of the Jet Propulsion Laboratory, tasked first with finding ways to automatically recognize wheat fields and later to estimate beaver populations by looking at how the shape of a lake changes and finding the patterns that pointed to beavers. Here, of course, the changes in the lake become a proxy for the number of beavers. In his view, and that is why I put this on a slide at all, this is essentially still how big data works today. You find correlations and predict, in this case, the amount of beavers, not always accurately, but often accurately enough from the changes in lake shape. That is, you recognize the patterns that beavers create when building dams. If it actually were beavers who changed the shape of the lake, or why beavers gathered at this particular lake, or how many there are exactly, you might never know. Here, big data is always already mediated or indirect in a different sense, providing a correlation by proxy, not a mirror or image of the world. And yeah, how proxies made it into scientific reasoning, I think, is its own fascinating story. Big data emerges around direct practical purposes, as I just said, and mainly around pattern recognition for military or government, controlling populations, tracking agriculture at home and abroad, and around prestigious projects with possibly huge economic implications, such as expansion in space. So we're talking about satellite images, or in Pentland's case, images taken by a plane of around 2 to 3 images per second. It is in these laboratories that data became big, and only, as I said, in relation to the processing power of the available supercomputers during the 1960s, when data gathering from above became easier and more interesting for military and government purposes. In the context of these huge federally funded research institutions, big data designates an effort to map the world. The data collection processes quickly outrun systems capacity, but they do not stop. It likely goes without saying, but I would like to make sure that this is clear, that of course, What counted as big then, or in the early 1990s, or even in the 2000s, is dwarfed by today's data sets, even relatively well-controlled corpora of data such as WordNet or ImageNet, let alone LLMs. Since around 2012, there are many definitions of big data floating around, but they all revolve around both the epistemological quality of big data and its materiality, and they often still tie big data to what was seen as an information overload or even an information deluge if they lean towards the negative, and on the positive side, the almost magical power of correlation, as we have seen in Anderson, but also as we can see here. The three V's, volume, velocity, variety, I think is the most influential definition that is everywhere in quote-unquote data science. And all other definitions provided from within industry context remind us of these properties of big data as an effort to map the world and do so in real time. So now let's turn to big data as an approach. So how did big data become an approach to artificial intelligence? There is no data like more data. By the late 1960s, actors remember a crisis breaking out in natural language processing. The premises and hopes related to the field had for the most part been disappointed. Researchers in the laboratories in the 1950s had set out to create a machine that would react to voice command or even understand speech, although definitions of what understanding meant strongly differed, and we can discuss this. And they thought, or were sure, that a voice-operated computer could be built within the next 10 years. Obviously, they failed. It is clear today that in the early days of computing, often senior researchers in the field thought that what they thought was easy for humans, i.e. speaking and conceptualizing the world through language, should be easy for computers too. Today, it's pretty clear that this is not always the case, but it's interesting to think that the engineers working at the laboratories really thought that they could make speech understanding in a strong sense happen. While the whole project of artificial intelligence research at the time often revolved around mathematical proof or games like chess, and then later Jeopardy and automatically generating, as I just said, proof. And we've heard two presentations about that by Thomas Hay and David Dunning here. So researchers at this time saw proof of intelligence more around mathematics. However, natural language processing was of course part of the initial program of AI as laid out in the Dartmouth project. Just not a very either maybe prestigious or, as we know today, achievable part. So by 1969, John Robinson Pierce, the head of speech recognition research at AT&T and director of the Federal Automatic Language Processing Advisory Committee, a federal body, had had enough. Pierce, anyhow, it seems, has never believed that computers are good at the same things that humans are good at, and in 1969, he brought forward the now infamous in the field Alpac report urging the government to stop funding the field he's working in, and at the same time wrote an op-ed for the renowned journal at the time of the Acoustical Society of America. And so he says, it is not easy to see a practical, economically sound application for speech recognition. The arguments given earlier may lead us to believe that performance will continue to be very limited unless the recognizing device understands what is being said with something of the facility of a native speaker. That is better than a foreigner who is fluent in the language, and that is a rather striking goal right there. Next to the economic considerations, which are at the heart of Pierce's argument, what I would like to draw out from this quote is that Pierce believed understanding, actual semantic understanding, has to come before successful speech recognition can happen. That is, understanding is a prerequisite, in Pierce's view, to actually successfully hear, especially in a loud environment like traffic or the battlefield. And that is what people at Bell Labs thought of when they were building speech recognition applications. The economics Pierce mentions speak to the question of how much processing power and data would be needed to enable a system to understand language. Due to his prestigious position, Pierce was able to cut funding to speech recognition research in the early 1970s. Although, as we also heard here before, the narrative of an AI winter from the late 1960s and early 70s onwards, often presented by actors, should be viewed with caution. Funding was still going into a lot of applications that were technically, or as laid out by the Dartmouth program, part of artificial intelligence research. Scientists simply avoided the term AI for a time, and now we're seeing the reverse. It might have been in part the stifling of research at AT&T, their biggest competitor in a way, that maybe led IBM to pursue speech recognition research further. In 1972, they founded a research group, the IBM Continuous Speech Recognition Group, to create what they called a voice-operated typewriter. The electronical engineer and information theorist, not a linguist, Frederick Jelinek, was picked to lead the group, and he was joined by Lalit Bahl and Bob Mercer. Mercer is a physicist with a strong expertise in computers and computer processes, and later biased Cambridge Analytica. Bahl, equally as Jelinek, is an electrical engineer with an interest in information theory. Mercer and Bahl come out of Urbana-Champaign, and Fred Jelinek is trained at the MIT. Mercer, in particular, also begins to work closely with Peter Brown, also a physicist, whose PhD is supervised by Geoffrey Hinton. Brown joins IBM only in 1983, bringing lots of corpora data with him, but I'll get back to him when we're there. All of the researchers that I mentioned come from institutions that had access to supercomputers. The work of the IBM Continuous Speech Recognition Group would not only change approaches to AI, and when researchers within the group started to cooperate, again with groups working on language processing or automated translation, at AT&T and Carnegie Mellon University, they would change the field of computational linguistics by providing the field with a statistical approach, but more importantly maybe, with evaluative practices related to that approach. When we're looking back at his time at IBM on the occasion of being awarded the Lifetime Achievement Award of the Association of Computational Linguistics, so here clearly this approach has left industry, Jelinek provides further incentive for IBM to invest resources in speech recognition in the 1970s, and I quote, "Why did IBM start research in speech recognition? Believe it or not, IBM was worried that with the advance of computing power, there might soon come a time when all the need for further improvements would disappear and IBM business would dry up. Somebody came up with a suggestion that speech recognition would require lots of computing cycles. So the idea at IBM was that all businesses, research and state institutions who at the time could utilize and needed computers might already have them, and would not therefore not soon buy more computers or look for better hardware. Instead of, or while also possibly thinking about personal computers, they hope to create what Jelinek calls a killer application. An application that would replace secretaries in a business context and therefore be highly attractive, and at the same time, and that is what makes it a killer application, rely on its own hardware environment, because it would need, as Jelinek says, a lot of computing cycles. So that is, it would need to process a lot of input data. IBM, after all, sold data processing solutions. So the interest in speech recognition at IBM had not much to do with creating anything intelligent or the prestigious project of AI and language understanding research. They hoped to make money by replacing labor with hardware, thereby creating a new market for a resource-intensive application. The more computing cycles, and therefore the more resources the application needed, the better. Yet, as I noted before, language processing and in particular language understanding are intimately connected conceptions of AI in research and science fiction alike. Now, the usual way of building language processing applications in the 1970s, of which IBM, of course, was aware, was rational or called rational or even rationalist, or the so-called expert systems approach. Following the publication of Syntactic Structures in 1957, where Chomsky presented in his own words an anti-empirical project, and his subsequent work on formalized grammars, as well as rational thought and philosophy, research in the emerging field of computational linguistics and NLP in the US turned almost completely towards trying to encode grammars and clear rules derived from theories about human language generation, understanding, hearing, and more generally cognition. And the UK and France are really different. So this is the US, but the US kind of influences the developments in the whole field. The use of the notion rational points to the fact that Chomsky accepted a brain, computer, or mind-machine analogy as a premise. Very broadly speaking, the languages of empiricism and rationalism have accompanied research in machine intelligence from the beginning and before the notion of AI existed. I would like to briefly note that I view these actors' categories as more or less umbrella terms. However, many different empiricisms and rationalisms existed in the work with computers, and I think it's useful to take actors seriously in using these terms and understanding how they use them, because these epistemological, ideas or even ideologies or whatever we want to call them, often seem to anchor how actors go about building applications and work with computers. And of course, these practices equally change, concepts of empiricism. So very broadly speaking, empiricists working with computers believe or understand that the human mind is based, or human understanding is based on data, And Alan Turing, for example, cites Locke as guardian of his intellectual tradition when he writes, instead of trying to produce a program to simulate the adult mind, why not rather try to produce one which simulates the child's? If this were then subjected to an appropriate course of education or learning, one would obtain the adult brain. And we'll hear a lot, I think, about also educational practices around the computer, and this would also be an interesting question of how this influences ideas of education, right? Presumably, the child brain is something like a notebook as one buys it from the stationers, rather little mechanism and lots of blank sheets. Let's put aside the fact that this is, I think, a very striking presumption. It is clear that in Turing's view, the brain appears to be without, or nearly without structure, and it learns from data. The exposition of data comes first. Chomsky, throughout his life, takes the opposite view and later develops it, arguing for the existence of a universal grammar and the idea that we are pre-coded to have a language faculty. I'll not get into this debate much further. However, the idea that data has no fundamental but a secondary role in how children learn to speak already guides Chomsky's work in syntactic structures, although he coins the notion poverty of the stimulus argument later in the 1960s, where he already explicitly argues in syntactic structures. He also already explicitly argues against behaviorist conceptions of learning and information theoretical understanding of language as a Markov source. The idea of language as a Markov source is taken up and developed by Claude Shannon, the quote-unquote father of information theory, and Warren Weaver in the 1940s. Modeling language as a Markov source becomes a key practice in a variety of research laboratories and points to the fact that Shannon's influence, or as one of my actors puts it, spirit, never really went away, despite Chomsky's considerable influence on the more linguistic-prone parts of the field. And small side note, I mean, to a degree, this seems to be an ongoing debate, or at least Geoffrey Hinton thought it was still kind of like worthwhile to go up against Chomsky when he was being awarded the Nobel Prize in Physics. Very broadly speaking, a Markov chain is any process in which one state can be, well, predicted with higher accuracy and where the previous state is known, and language clearly is such a source. If you know the word that I've previously said, you might be better able to infer what word I may say next. A Markov source is a source of information where the underlying Markov chain is hidden, and we'll get to back to the hidden part in a second. But first, let's be clear that Chomsky does not deny that language can be modeled as a Markov chain, or that it can be thought of as a Markov source. He thinks, and here we come to the question of scientific standards and the aim of research projects, that this way of looking at language provides no insight into how humans actually understand or generate language, and hence is fundamentally uninteresting to linguistics as a science, and possibly the project of AI by extension. The statistical mechanism to Chomsky provides no insight in the mind, and furthermore, as a simple mechanism, also no theoretical insight into language as a phenomenon. And there is a wonderful book that I was alerted to here called The Automation of Language by Jacqueline Léon, that kind of like maps out this broader discussion between Chomsky, Yoshua Bar Hillel, and Shannon, and what she doesn't do is look at industry. So the engineers who were chosen to lead the IBM group are not linguists, which I think is an interesting choice on the part of IBM, nor are they necessarily interested in language. They're information theorists and physicists, and hence they begin developing their approach from Shannon's noisy channel model of communication and the idea that spoken language can be effectively modeled as a Markov source, no matter if that provided any insight of note into the phenomenon of language more broadly. The noisy channel model proposes the following model of communication. Language begins as concepts in speakers' minds. They are then transformed into an unreliable, hard-to-codify medium, namely the sound wave that we create when we speak. That is the noisy channel plus any background noise. The sound wave then is decoded as concepts, again, for example, mediated as written text. That is what IBM wants when they generate a typewriter, or as heard by another speaker and transformed by her brain. So two things are important here and draw us into how data become the most important means to create this type of language processing application, and I'm sure you all know that. So we only know the concept formed in the speaker's head through the unreliable source, right, speech. If we conceive of language as a Markov source in which the original source is hidden, then we have a probabilistic problem that can be solved with training data if we can assign probabilities. Then we can train the models on sounds and how these sounds relate to text. The clear algorithms that were implemented at IBM into hidden Markov models and growing corpora of data are first the forward-backward backward algorithm developed by Leonard Baum and Lloyd Welch at the IIS in Princeton, most likely in the context of decryption. And much later, Bob Mercer and Peter Brown developed the maximum mutual information estimation algorithm that, according to Brown, informs Geoffrey Hinton's and David Romelhal's work on neural networks. Basically, it allows for the estimation of shared information between two hidden or unknown variables, which much later becomes important in deep learning. So all of these algorithms are useful to find or rather create, I think, patterns in unknown data. But back to Markov models where the input is hidden, similar to the hidden layer in neural networks. And in fact, hidden Markov models are a special case of a very small, very small time-sensitive Bayesian network. If you can utilize enough training data, then you can figure out the parameters of transition for different states. So the IBM group begins to collect all types of language data they can get their hands on to create large corpora of data to train their hidden Markov models. And I think by the end, so by the late 1980s, they were able to train 3-gram models. There are other than today criteria for how the data was created, but diversity or volume was key. As Mercer exclaimed in 1985, there is no data like more data in this approach. And as Xiaochang Li points out in her PhD dissertation, this is a striking endorsement of quantity over quality of data. In addition, the use of training algorithms such as the maximum mutual information algorithm traveled via the research of Peter Brown to research in neural networks. Brown was Hinton's first PhD student, and according to him, they spoke about how models learn from data all of the time. It's important to note that Brown has a background in physics and the application of information theory that is further detached for Hinton, who was trained in psychology and AI. And it's also kind of important to note that it is the maximum mutual information estimation algorithm that kind of becomes the key to everything because it allows for the statistical generation of tokens, the automatic generation of language tokens. Data became the key resource to build models at IBM, and this is crucial because it's noted the standard approach to language processing and AI at the time proceeded via predefined linguistic rules. To cite Brown, the primary connection between the IBM work and artificial neural networks is the concept that AI can be accomplished through the maximization of a clearly defined object function on data rather than specifying rules. When we got started at IBM on language modeling and translation, most people were doing AI through expert systems based on human-specified rules of linguistics. We took another approach based on mathematics and data, and this approach is now what modern AI is based on. One could question what mathematics here is, but I think that is a different presentation. So what does it mean to replace hard, explicit, accessible rules with parameters estimated from growing corpora of data? To Peter Norvig, who was until 2023 the head of AI research at Google, this shift in interest is also what made modern AI possible. According to Norvig, writing in 2012, complex phenomena cannot be rendered computational through the use of hard rules. Importantly, and possibly not consciously, Norvig always already speaks about language use, and from there concludes that all of language is what he calls a complex or probabilistic phenomenon. It is clear from what Norvig says that language to him appears as a phenomenon that can never be captured fully by rules. So he says, language is a probabilistic phenomenon, so probabilistic models are best for understanding how humans process language, and here we have also clearly an equation between the system and humanity. Since people have to continually understand the uncertain, ambiguous, noisy speech of others, it seems they must be using something like probabilistic reasoning. Chomsky, for some reason, wants to avoid this, and therefore he must declare the actual facts of language use out of bounds and declare that true linguistic only exists in the mathematical realm, where he can choose the data modeling formalism he wants. This may be very interesting from a mathematical point of view, but it misses the point about what language is and how it works, and here language use becomes language. So we can see here how language becomes, in Norvig's view, just a probabilistic phenomenon, and how language in total is equated with language use. According to Norvig, the best we can do to capture language as a phenomenon is essentially parameter estimation and often very successfully predicting an output from an input, given a hidden source or not. However, that of course defies what, for example, Chomsky sets out as an ideal for computational linguistics as a science, where the aim is to gain a better understanding of language, and ideally of language as it appears to humans, in order to arrive at something akin to human intelligence or human language understanding by technological means, artificial intelligence research, or just an explanation of how and why language works. So two different scientific ideals, if this one is a scientific ideal at all. And it's important to remember, given the current hype around AI, that what large language models model, and very successfully so, is not language broadly, but given their training data, language as it appears on the web. In addition, there are no representations here, or to put it differently, we usually think that models, even statistical models, say in climate science, should represent, and they give us a representation by providing a statistical mechanism that links the data back to a phenomenon. And that is partially the case in IBM's work, who still had a clear statistical framework, and it is much harder to show how this is the case for probabilistic neural networks, which is why people, I think, are starting to throw category theory at all of this. So let me go back briefly in the interest of presenting a historical ontology to the context. So IBM had an economic interest and essentially wanted to build an application that would work good enough in the office context and need a lot of processing power. As the approach presented by IBM became successful, which happened only after around 15 years of research and constant increasing in computing power, it changed the field of computational linguistics as well. Now, linguistics is arguably should be concerned scientifically with language, and actors from actors from within IBM speak of an empirical paradigm shift in computational linguistics that is closely tied to the later successes of machine learning. It is also independent of scientific success, however we might define it, but rests on the successful implementation and usability of the application built. To cite Mark Lieberman, who is a computational linguist working at AT&T in the 80s and very closely associated with the IBM group, going back to Pierce's article from 1969 in his obituary for the group lead at IBM, Fred Jelinek, I quote, "And this history now puts us in a position to apply John Pierce's perspective back to front. Like most of the rest of his generation, Pierce felt that the natural progression was for scientific understanding to serve as a foundation for engineering applications. That is, Pierce wanted language understanding first, but instead, more than 3 decades of engineering development in human language technology may now permit rapid scientific progress. Hence, what comes first, in Lieberman's view, is the ability to show things or generate language statistically, which might allow for a new form of scientific insight in his view. Chomsky, to this day, of course, disagrees that this method helps generate actual scientific insight. However, with the advent of statistical methods in computational linguistics, came quantitative and quantifiable standards introduced by Lieberman and Jelinek via the Common Task Framework. So the Common Task Framework still today is one of the key evaluative frameworks or practices within machine learning. It provides a shared task and test data on which the performance of different applications can be tested and then tweaked. The implementation of the Common Task Framework became in the 1990s a prerequisite for getting funding by the Defense Advanced Research Projects Agency in the US. Then the paradigm shift, the change of research practice and research aims, was not just an effect of the success of the IBM approach, and it did work better than its rational counterparts, there's no question. However, it is equally the effect of a new quantitative regime of evaluation and funding pressures pushed through by the biggest US funding agency in the field. Looking back, Bob Mercer notes that likely this research would have developed elsewhere and more quickly, and I would like to suggest possibly in different directions if research institutions such as universities had the same data processing capacity and access to data that IBM had. Hence, big data as an approach is only possible from within industry and tied to vast economic resources and a direct interest in an application that runs and no interest in direct scientific insight, at least. Research actually explicitly and proudly distance themselves from any effort in linguistics and self-identify as engineers. In one of my favorite quotes of computing history, Jelinek puts it like this: "We thought it was wrong to ask a machine to emulate people. After all, if a machine has to move, it does it with wheels, not by walking. If a machine has to fly, it does so as an airplane does, not by flapping its wings. Rather than exhaustively studying how people listen to and understand speech, we wanted to find the, and here we go, natural way for the machine to do it. The natural way for the machine at IBM, again, according to their own self-understanding, a data processing company, turned out to be, maybe somewhat unsurprisingly then, data-driven research. Moreover, the language data that had been painstakingly generated, often at high costs, was broken into, as I just said, ideally processable parts for the available computer system. And here data, I think, becomes equally an expression of the given computer system as well as of the phenomenon that is traced. As the research and importantly algorithms traveled to neural networks and neural networks became probabilistic or rather data-driven, I believe the brain metaphor or human-machine analogy that Jelinek saw as harmful for working with computers was reintroduced. Today, some people within the industry argue that humans might also just be stochastic divination engines, or to use a term coined in a critical effort by computational linguist Emily Bender, we just are stochastic parrots. So it is no longer just language or images that are technically generated. We ourselves have become probabilistic phenomena consisting of data. So what I hope to have pointed out by this narrative is that big data as an approach became a way to see the world and conceptualize phenomena, and arguably intelligence, and via intelligence ourselves. That goes beyond the rather well-researched context, I think, of big data in the state and surveillance. It is an interesting question to me how big data as an approach or method makes the view of big data as a more complete mirror of the world, or even as Pentland puts it, a God's eye view possible. In an interesting way, Norvig seems to accept the perspective of the computer system when he describes language only as a probabilistic phenomenon, and probabilistic here for the most part translates as Bayesian. Here the gap between language as a phenomenon and language as computationally recreated disappears. It seems, thanks to automated data processing, data has not only become a building block of facts created about phenomena, but of the world as it is. Everything is also data, or to put it slightly more accurately, can be captured as data and subjected to probabilistic prediction. This worldview emerges, as I said, within the context of Cold War industry, most importantly the biggest tech companies at the time, IBM and AT&T, and it is from the beginning tied to what is called by actors an economic imperative. The idea was to sell hardware systems or make an application that could only run on the associated hardware. The links to industry practices, even today, where if you want to participate in AI or build your own AI application, you have to rent server time, get access to training data or foundational models, like Lambda, which capture you in the infrastructures of large companies such as Meta, still, I think, make AI a killer application in the way Jelinek uses this term, reliant on its own hardware infrastructure, and we therefore are still buying access to the hardware infrastructures of the industry. And it's worthwhile to note, mentioning the vast infrastructures that we use about 1/4 gallon of water for every query we enter into ChatGPT. That's according to researchers at Google Research. And moreover, we trust these probabilistic systems to provide more or less reliable access to facts. And I would like to suggest that classic information retrieval was a better tool for that than the probabilistic generation of answers and phenomena from web data that we see now. Yet, I think the sciences are changing to include ever more of these tools as well, and I think that is an open-ended effort. Thank you so much for bearing with me.
Very much. Do we have any questions?
Thank you for the talk. I have a question because some statistician goes with the slogan that data don't lie. But I keep arguing with them that why I'm taking this is because most of the AI models are based on probability statistical model. But still, some of these models, when we use them in mathematics, we see that there is no accuracy. So that's what I'm asking today. Is it really true that data don't lie?
Well, I think this whole presentation was kind of an effort to say it depends, right? It depends on the context, it depends on what you want from data, it depends on how you generate them. And clearly, data can misrepresent phenomena, right? So they can lie, if you will. So to me, I think you're right in your discussion. I don't know. Is that a useful answer?
Yes, I'm thinking because the way to solve the problem I'm thinking is that we need more mathematical approach to AI. Why is because I'm looking at it is that when we talk of precision and accuracy, we need to look away from the classical algebra, binary algebra to fuzzy algebra. and most researchers are not too familiar with such work.
I do think that, I think part of my argument outside of history would be that, yeah, clearer theoretical frameworks would help, and that to me is what you're describing. And I think if you're looking for people who also kind of look into that direction, I think Gianni Gastaldi, who was here earlier, and Thomas Seiler are kind of like thinking through how to kind of provide a theoretical framework in which, you know, you can make more clear how neural networks work and what the data structures within a network actually are. So maybe talk to them about this further. So yeah, thank you for the question.
Do we have any more questions? Okay. Yeah.
Yeah. Thank you, Amira. So you showed this quote of Chomsky, right, about the cognitive structures. So I wonder if you could just say a little bit more about how Chomsky's theory of cognitive structures fits into the history of data-centered AI that you were telling today. Am I correct in understanding that Chomsky is just a completely different approach and has no connection to the data-driven AI, or if there is a connection, what's the connection?
Chomsky is really interesting in different ways, and I think has actually kind of a prehistory in statistical work, as it's done kind of in the 1950s at MIT in linguistics. And that would be in Jacqueline Lyon's book. And he turns against that, but I think for reasons of conceptualizing science, and how he understands kind of what the ideals or goals of science. And his approach, again, within something that I would call computational linguistics, maybe versus natural language processing, it becomes very influential, but these two terms to me at the time are also still in flux and up in the air. And to me, I mean, I'm kind of like using him maybe a little bit too much as a straw man, but kind of as this big, big figure that all of these people are still arguing against, because to them, he becomes kind of the person who creates or who pushes the expert system approach. And it is also interesting that despite their like very, very different politics, John McCarthy and Noam Chomsky, so John McCarthy is a right-wing Republican, right? They kind of meet on the computer-brain analogy and on the idea of like that you need logic and expert systems and clearly provable science, and a very kind of like clear formal idea where, you know, science follows mathematical proof versus, you know, the people at IBM and at Carnegie Mellon who would start to employ data and statistics.
Ursula, did you have a question before?
I think actually, I was going to phrase it differently, but I think you more or less answered it. But
okay. Sorry. Yeah. Go ahead.
I want to go to the third of your points in the conclusion, to ask you to spell out a bit more the respect in which the story that you've been giving us goes beyond conceptions of surveillance or data capitalism. What does the probabilistic approach do that you don't see in those other ways of looking at it?
I mean, I think in a way, it's a way to, so surveillance to me is still an effort of mirroring the world. And I think in these kind of AI applications, we have the generation of new phenomena. I think data is a probabilistic phenomenon, language is a probabilistic phenomenon, for example, is something else, and that is precisely where you can point out if you look at the conversation that Hinton is still having with Chomsky or Novick is still having with Chomsky, right? And so in that sense, I think in actually generating a different type of phenomenon, it goes beyond like the pure notion of surveillance and beyond the mirror. And also I think it is important that in the beginning, if there is no direct interest in knowledge about something, then maybe that is different too. I don't know if that's an interesting answer at all.
I think there's lots there, and as you're describing it, I'm wondering about the perspective of the person surveilled, who might actually be in a situation much more like the one that you're imagining, come from the probabilistic.
Yeah, no. I completely agree that surveillance also creates people, right? That's the whole idea of data doubles. But I do think maybe we can look a little bit more closely at how these phenomena, say the data double, comes about. I think that's the idea, and detach it also.
So I can ask a very naive question. Is this very much just an exclusively US story, or is there anything going on elsewhere?
I think it was a US story, and now is a story everywhere.
Any other questions?
Just to comment on that, Chris. At some point in the in the endless discussions about how the UK government is going to empower everybody by AI and various kinds of rhetoric, there was sort of talk about what's called sovereign AI capability, which means that the UK will invest in a dream that the UK will invest enough to match what Google and co are investing. Well, it's just a ridiculous dream because the UK, I think somebody figured it out. They were planning to invest what Google invested every 6 months, and that would be it. And so it plays out in that kind of rhetoric, and how that kind of rhetoric was. We were having a discussion one tea break about what happens when policy is driven by tech bros. But at the same time, you look at what's happening in China. You look at the DeepSeek. You look at it's not just a US phenomenon, but a lot of the writing and thinking about it, the US writing and thinking about it is more accessible than what's happening in other places.
Okay. Any last questions? No? Okay. We can stop before we get down to the dreaded 0, but thank you again.